We're here to talk a little graphical analysis. We're going to analyze graphs individually. So we have an x versus t graph here, and we're going to talk about what that means. And then in addition, we're going to compare it to velocity versus time graphs and acceleration versus time graphs so that we can see how the different graphs illustrate the exact same motion, right? Or in this particular case, a lack of motion. So if we have a displacement or position versus time graph, and that's a horizontal line, well, what that's saying is the position at any of these times is exactly the same. So therefore, the object whose motion is being represented by the blue graph here is not moving at all. Now, if I make a red line that looks like that, since that red line is horizontal as well, then the location of the object whose motion is represented by the red line is the same, right? The location for this red object, let's just say, is the same no matter what time we're talking about. So that means the motion for this object and this object are exactly the same. The difference is where they're located. So if we have some zero location, so let's say I'm at zero location and this is positive and this is negative, right? The blue object, let me put my blue marker, the blue marker might be located right here, right? I'm zero, the blue marker is right here. That's the motion of the blue marker, right? The red marker, maybe over here, is represented by that. Neither one of these objects is moving. This is closer to the 0 point than the red object, right? Well, what about the black? What about the black marker? What if I put the black marker right here? It's not moving either, so we're going to have a horizontal line, but something's got to distinguish it from these things. Well, what distinguishes it is it's in the negative. If these things are in the positive, this thing is in the negative. So therefore, the position versus time graph for something like that would look like that. It's down in the negative. Now, none of those objects are moving, right? So if I wanted a velocity versus time graph or v versus t graph, well, that velocity is going to be right here on the 0 part, right? Like its velocity is 0. It's not moving. So the graph for velocity of any of these markers or objects that's represented by this is going to be 0. Now the acceleration is also 0. Important for us to note is when we go down from x to v to a, we really want to only look at the graph above it, right? So why? How am I going to tell acceleration? Well, I'm going to take a look at the velocity. And since acceleration is a change in velocity, we see here that velocity is not changing. So therefore, my acceleration is also going to be down here, right? But this acceleration being 0 isn't necessarily due to this thing being horizontal. It's due to this thing being horizontal. Since the velocity is not changing, then our acceleration is going to have a value of 0. All right, now let's make this a little bit more complicated. Let's follow our same setup here. Here's position versus time. And let's just say that we're talking about an object whose motion is that. All right, well, what's happening here in the motion of this object, okay? Well, x is increasing as time goes on, so that's important for us. And very specifically, we say that it's increasing at a constant rate. So I'm gonna leave that up there and redraw it real quick down here because I'm gonna erase it eventually down here, but leave it up here to do some comparisons, right? So look at what that means. X is increasing at a constant rate. Well, what that means is this. If this is a particular time frame right here, then the change in X, that's this right here, delta X, over this particular time frame here, delta T, that change in X for each particular time frame, if I keep the time frame the same, right, there's delta T, here's my delta X, there's my delta X, every particular delta T that's the same has the same delta X. The rate of change of displacement is constant throughout this entire interval. Well, what is the rate of change of displacement? It's velocity. So if x is increasing at a constant rate, the significance there, therefore, v is constant. Not only is v constant, but again, if v is the rate of change of displacement, then the rise over the run is my displacement of x with respect to t. So if v is constant and v is delta x over delta t, right? Now that's average velocity. Then this average velocity then is the slope of an x versus t graph. And that's super important for us. Okay, well, what about blue object? All right, blue object's motion looks like that. Now I'm drawing this freehand, so it might be a little bit off, right? Now, my intention here for blue is that it's the exact same motion, right? So if the slope for blue equals the slope for black, then they're telling us the same exact motion. So, freehand, they're not exactly the same. They were meant to be the same. The motion of the object represented by the black line is the same as the motion for the blue line. There's a difference though, right? They started at the same spot. They just started at a later time frame. So blue started at the same spot, but at a different time. The spot is x equals 0. Here, the time is 0. Over here, the spot is x equals 0, but the time is something other than x equals 0. Well, what about this? What about this object? What about this object here? The red object. Same slope as black, same slope as blue. So the speeds are the same, the motions are the same. What do we got different here? Well, black started at x equals 0 at time equals 0. Red starts at x equals something at time equals 0. So while blue started at the same spot at a different time, red starts at the same time, different spot. Now I'm gonna have to erase this blue stuff here to clean this thing up. I'll keep the slope part because the slope part is super important to us. Well, this is the hard part. When we start going from one to the next, from x to v, that makes this super hard. So, what do we know about the slope of this black line? The slope of the black line is constant and positive, and the slope tells us velocity. So if the slope of this black line is constant and positive, then the speed represented by that thing is constant and positive. Now, let's talk about a couple differences. What happens if I have this as my graph? Now, we're traveling, so here, this object, let's call it black up top here, starts at x equals 0 and moves towards the positive. Blue starts at x equals -2 and moves towards the negative. The slope of this line is constant and negative. And if the slope of this line tells us velocity, then my velocity is going to be down here below the axes. Positive velocities, negative velocities. What do the signs on velocities tell us? The sign on velocity tells us direction. So we got all sorts of different possibilities that can happen here. Positive slope that's constant, negative slope that's constant translates into a positive constant velocity and a negative constant velocity, meaning different directions of motion. Now, one last thing for us to say, right? What about, I don't like crossing my markers, so let's do that. What about this line, right? Oh, what about an object whose motion is represented by that red line? Well, its slope is constant and negative, just like the blue's slope is constant and negative, except the value of this slope is much higher. What's that mean? Well, it's more negative, so my graph would end up down here, and the bigger the slope means it's going faster. So this object here that's marked by the red line is going faster than the object that's marked by the blue line. And quite frankly, even though maybe this is maybe 10 meters per second negative, and maybe this is 5 meters per second negative, and this has a positive maybe 5 meters per second, remember the plus and the minus only tell us direction. This object's actually going faster than something with a plus 5 meters per second because the plus 5 up here only tells us direction. Now, how do we get acceleration off of this? Well, I've got an acceleration graph as a function of time that tells us what's acceleration. It describes the change in speed or the change in velocity. Well, what kind of change in velocity do we have here? Well, what kind of change in velocity do we have over here? We didn't have any change in velocity, but we have no change in velocity here, here, or here. So all of these things also have an acceleration graph that looks like that. Why do we have an acceleration graph that looks like that? Because we have displacement that is changing at equal rates as time goes on. That is a constant velocity. A constant velocity is zero acceleration. So in order for us to have some value of x that is not zero, right? In order for us to have a value of x someplace, we have to have a displacement that is not linear. Any type of curve on an x versus t graph is going to ultimately lend itself to some values down here in the acceleration. And that'll be the next step for us when we talk about graphs of accelerated motion.